Ready? Hello, everybody. Welcome on class. Is it 4? Yes, 4. Code developer skills. My name is Tom Breza. I'm one of the hosts for C++ London Uni. We are a non-for-profit group. Another people involved in a project is Oliver Din, who is one of the co-hosts and teacher, and as well another one. The person who is now enjoying some a few minutes break is Tristan, and he'll be leading today's class. So, what do we have? I think I need to click here. Does it work? Yes! Okay, so first of all, big thank you to Mimecast for providing us with the free space. And as always, providing us with nice refreshments and pizza, which is amazing. Yes. So thank you very much. We really appreciate. Ollie, say thank you to your boss, and you are lifesavers in this case. Okay, the main boss at the top, so he knows about our existence. But as well, I would like to say thank you to all these people. They are our patron sponsors. They are people who decided to pay like recurring money to support us, and this money basically help us to improve what we're doing. Yes, buying mics and so on. So a massive thank you. That means somebody's paying more than anybody else. We are still looking for some space. Now, I got a bit of positive development here. One of the larger businesses might offer us a bit of space, like ever so often. But we are trying to work out, with them details and so on. They got lots of red tape, and we're trying to, go around that. But if you do know someone who can help us, please do spread the word, because I can't do it on my own. Yes, the beauty of the open source and charitable project is that it's not only 2 or 3 people who are doing the work, but the whole community. And that means if you want to have the classes for which you don't have to pay, you have to do some work. That's one of this. Without this, the project doesn't exist. So please do help. How do we work? We work, as you know, basically twice a week. We try to meet up. On Tuesdays, it's what you have now. It's a lecture, so we'll show you something new, interesting. And on Thursdays, you meet with one of the experienced developers, and you have the chance to try this on your own. From what I know, the feedback I'm getting from Ollie, in recent weeks, that's become very unpopular. Look, if people stop coming on Thursdays, yes, they will be here like a massive red X, and we'll stop doing that, because what's the point of wasting time? So if you don't want it, if you don't see the benefit, it's almost like you're missing on one-on-one with the experienced developer, which costs something like, I don't know, £100 an hour, and you have it for free, for cost of coffee. Your choice. I was coming regularly, but I've been away from the country. That's not an excuse. Okay, now another part. Again, I'm sorry it's boring, but the thing is, we can't survive without that. That's the reason we're saying it. How can you help us? If you decide you want. The first one, obviously, is the most obvious. If you're working, if you're not on some sort of benefit, you have wages, and you not some difficult situation, and you benefit from this. Yes, it gives you something. Please consider becoming our sponsor. You can pay a few pounds or a few £100. It's up to you. Yes, obviously we don't expect to go crazy, but any money you pay, it's going to the good use. Second, obviously sponsors. So maybe Facebook, maybe somebody who would like to have a good image, that it helps the communities please do send them in our direction. And finally, after the class, as always, we're going to the pub. And it's not a very nice thing if two people, for example, from the students suddenly have to make sure Tristan and Ollie look after. Yes, when too many people disappear, because paying out of your pocket every week £20, yes, it's expensive. If it's a whole group, it's £2. So, but I leave this into your hands. Another thing, this is more to help you. If you decide that you need a memory stick which is with multiple working operating system, so basically you have, let's say, a company laptop, or you don't know how to set it up, all the compilers and so on, or you don't have time, consider buying one of these. You plug into your laptop, the machine will start, and you have everything pretty much ready to code and to do exercises and so on. Interested, talk to me, Ollie, and we'll get you one.
Can you control the Russian Beluga well with the USB?
No idea. Social media. That's another way of you helping us. Spread the word about us. Whatever social platform you use, yes? Even emails is good, I know these really fantastic people. LinkedIn, Twitter, and so on. Please do. That always helps us. And then finally, the boring stuff is over almost. Please do check our website, because on the website you will find, I try to keep it as up to date as humanly possible. But if we book the class and so on, we have a space, it's there. So please do check and do RSVP. Just for your knowledge, maybe that's not clear. When we do RSVP, there is, I think, 4 or 5 hours cutoff time. Yeah, so if you don't RSVP X number of hours before the class, you might not be able to attend the class. And Ollie wants to as well add to that.
Yes, unfortunately, building security are getting a little bit annoyed with the situation, and this is going to be the last class where I'm going to be able to let people in if they haven't RSVP. So going forward, if you don't RSVP in time, I'm not going to be able to let you in.
Name's not nice, not coming.
Yeah.
So what's that, 24 hours before the...
No, I think it's at least 5 hours. But to be on the safe side, if you think you can cancel quicker, yes. If you think you'll come pretty much most of the week, just RSVP for more classes.
If you RSVP and you don't attend, then there's a printed badge that nobody uses, nobody cares. If you show up and then someone's got to do all the signing, then they get annoyed. So
That's fair enough.
So this way, basically, you can make sure that you get inside, because the insurance people, they're not fun people. They don't care kindly, that kind of stuff. So that's all from me. I apologize about ranting and so on, but I'm passing you to a very clever person, and he will tell you much more about CMake.
Right. Thank you, Tom. Yeah. Woo. Hello. Good evening. Hello. Welcome to session 4 of Core Developer Skills. So before we crack on, it's my usual opening slide about feedback. I think everybody's been here before, right? Anybody here for the first time? No? Well, then you've all guaranteed to have seen this already. But for anyone who's tuning in for the first time online, we do encourage you to join our Slack channel. Please do head to that link that you see on the screen, slack.cpp.al. Register with that, and then you can join us on Slack, and you can chat to us, and you can tell us what a great job we're doing, or not doing, or, you know, all of that stuff. So let's talk about this module. Again, you guys have been to the last few sessions, so you know what it's all about, but I'll just go over it anyway. So we're calling this module Core Developer Skills. Something a little bit different for us, something we haven't tried before. We're not teaching you any C++, or not any new C++ anyway. All the C++ in this module is relatively simple, relatively straightforward, stuff you have hopefully seen before if you've been to our sessions. What we're trying to do instead is to teach you, or show you some of the things that are useful in sort of real life development, things that are not directly C++, but things that you don't have to know, but are useful to know for your career as a C++ developer, where career might be just doing it for fun, but you know. So in the first couple of sessions, we looked at Git and at GitHub. Last week, we started looking at CMake, which we'll be continuing with today. We'll be looking at using the debugger. We're looking at continuous integration systems. We're going to have a little experiment on a session with common interview questions. It's going to be something quite different. It's not going to be like this with me, or not necessarily like this with me at the front talking to you, or Ollie. Might be sort of more of a one-on-one and more interactive thing. So that'll be in a couple of weeks' time. So if perhaps you've been to some interviews and you got some hard questions thrown at you, that would be unpleasant, thrown at you, and you're wondering sort of what would a good answer for that be, or you know, those sorts of things. If you can think of any good questions, then let us know. Perhaps on Slack would be a good way to do it, or you can email us if you prefer. Yeah, so those are the things we're currently planning on covering. I did have a couple more ideas. So yeah, that's what's on the menu for the next few weeks. If there are any other things that are not specifically C++ related, but you'd like us to cover, then again, please do get in touch. Okay. So, last time we were in the rather impressive offices across the road. Not that these offices aren't impressive. The view's just not quite as good. But last time we had an introduction to CMake. So, CMake, as I said, it's the most common build system that's used for C++ projects, certainly open source ones. It's probably the most common build system for proprietary, in-house C++ as well. It's just kind of hard to know. We looked at what a build system does, why we want one, why invoking the compiler yourself is a complete pain and you don't want to do it for anything non-trivial. We looked at the basics of configuring and building a CMake project. We had a little diversion about what a git ignore file is and how you write one, and how you can use it to get Git to ignore your CMake build directory and various other junk that your IDE puts in there. And then finally, right at the end, we talked about various build options, in particular the build levels, debug, release, rel with deb info, and the other one, min size rel. And we talked about different generators. So CMake actually relies on like an underlying build system. Yeah, I guess that's a way of putting it. An underlying build system that it calls a generator. So most commonly the default one on Unix is GNU Make. But it also has various other generators. So it can generate project files for Visual Studio and for Xcode and for a couple of other IDEs. It can use an alternative to Make called Ninja, which is often faster. It's very good. I like it. Ollie's not so keen.
I like it. It just depends how big your project is to justify it.
So CMake, in a sense, could be seen as a kind of abstraction layer on top of these lower level build tools so that you don't have to worry about the details of these platform specific build tools. So what's on the menu for this week is, well, we're going to talk a bit more about CMake. First of all, confession, I'm afraid I haven't had as much time this week as I would normally like to have, so we don't have quite as much material as I would normally prepare. Usually, you guys who've all been to quite a few of these will know I often do far too much and we don't get through all of it. Today it's the opposite, so we may be finishing early, which, you know, if nothing else, lets us get to the pub earlier, so yes. If we end up finishing early, then I do apologise. So anyway, last week we looked at how you build a CMake project. If you have an existing one you've downloaded off the internet or something like that. Today we're going to focus on how you actually create a CMake project yourself. So we're going to look at writing a CMakeLists.txt, or in fact what CMakeLists.txt actually is. We're going to talk about CMake targets, what a target is, how you define them, how you add them to your project. We're going to look at, well, one way, my recommended way, for how you should physically lay out your project. That is, where to put different files in different subdirectories and things like that. We're going to talk about what include directories are and how you link libraries. And then we're actually not going to talk about using third-party libraries because that's the bit I didn't have time to get to. So ignore that last bullet point. Sorry. Apologies. On the other hand, that would be something that would be quite good to do next week if we can also talk about VC package or Conan or something like that, because that would tie in very well. So perhaps it's a good thing that I didn't quite get to that. Anyway, that's what's on the menu for this week, for the next, well, perhaps a couple of hours, maybe a little less. You can all just spend a very long time on the exercise at the end. A little bit of revision, because today we're building on what we did last week. When I do that, I often include a couple of slides just briefly going over what we did last week, because we sometimes have new people who otherwise would be all so lost. But in this case, all of you guys were here last week. So we can just go through this pretty quickly. And of course, if you want to, if you are watching this online and you're feeling a bit lost, last week's video is available online on our YouTube channel, youtube.com/cpplondonuni. So you can go ahead and catch up on that one and then come back to us here. So when we use CMake, using CMake is a two-step process. First, we create a build configuration in a particular directory, which is usually a subdirectory or a project checkout. It doesn't have to be. It can live anywhere on your file system, but it's usually a subdirectory of the project checkout. And we typically call it build, something like that, perhaps build GCC and build Clang, and build GCC release, build Clang debug, ASAN, whatever you want to call it. It's just common to include the word build in there. So that's step one, create the build configuration. And step two is to actually instruct CMake to go ahead and call the compiler and the linker and do all those things that it has to do to actually, turn your source code into a compiled executable or library or whatever it is. So as we work on a project, we repeat the build step just to make sure everything's working. And many IDEs have very good support for CMake these days, including the recent versions of Visual Studio from the last couple of years handle CMake directly. C-Line is all built around CMake, and many other IDEs, Qt Creator and so on, all have built-in support.
So what actually happens with build step? It just checks the CMake list file and individual. I know we talked about it last week, but
Well, let me go into a little more detail for you, Sard, and perhaps things will become clear. So how do we actually accomplish step one, creating the project configuration? Well, first of all, we create a directory, just a plain old folder directory on your file system. You can use Make.dir, or you can do it with the graphical shell, or however you prefer to do it. Then we cd into this directory, and we tell CMake that we want it to create a configuration there. And the command for that is CMake, and then a path to the root of the CMake project, the directory that contains the base CMakeLists.txt. Which, if you follow this recommendation of having your build directory as a subdirectory of the project, you can just say CMake ... Nice and easy. ... for those who don't know, is a Unix shortcut, meaning the parent directory to where I am now. You can also use it on Windows DOS. So in the simplest case, we just say CMake ... But we can also add various configuration options. So one very common one is, oh, that hasn't formatted properly. Oh, how annoying. So we use -d define to set various configuration options that we want to use. That dash is right over on the right there, but imagine it's just on the bottom of that line, just before the D where it should be. So in this case, this example, we say -d and then CMake build type. Remember, as I said last week, there are 4 different build levels, build types that CMake knows about by default. The 2 that you're interested in most often is debug, which is the default, and release, which is use all the optimizations and make my code really fast. And there are various other -d flags you can specify. We can also specify which generator we want to use with the -g flag. It's -g and then generator name, like -g makefiles, -g ninja, -g xcode. Which particular generators are available on your system depends on a few things. Depends what operating system you're on. Depends whether you've compiled CMake yourself or whether you're using one of the pre-built options. But you can just type CMake -g with no other options, and it will list all the generators that you have available. Or you can do CMake --help, will also tell you. So that's how we accomplish step 1. How do we accomplish step 2? Well, normally from the command line, all we have to do is say CMake --build . So again, for those who aren't familiar with it, ... is a Unix shortcut, meaning the parent directory from where I am now, and dot is a shortcut meaning this directory. So CMake, please build this configuration right here. And of course, you could substitute dot for the actual build directory if you wanted to make life more complicated for yourself. So I mentioned that CMake is, in fact, sort of like an abstraction layer on top of these generators. And so when you call CMake --build, what it's actually doing is invoking make or ninja or MS build or Xcode build or whatever the underlying generator actually does. CMake --build is a shortcut for calling the generator. You don't have to use it. If you've specified a particular generator, you can go ahead and use the generated scripts directly. So on Unix, with the default, you could just type make in that directory, or Ninja if you've used the Ninja generator, or Xcode build if you're on a Mac, or what have you. Nope. Too far. So Sard, does that make things a bit clearer?
Yes.
Yeah?
Thank you.
That's all right. So are there any other questions about the stuff we did last week, about how you actually go ahead and convert an existing CMake project into an executable or a library, how you follow this two-step process? I'm going to assume everybody knows this, and we're going to go on and talk about some new stuff. Okay, excellent. Okay, so let's talk about CMakeLists.txt. So to use CMake, to have a project that uses CMake, we need to have a file called CMakeLists.txt. And at least on systems that care about case sensitivity, it needs to have this capitalization, and it needs to have the ending .txt. And this is a config file, sort of. It contains all the information about the project. What the project's called, its version number, programming language it uses, which targets it defines. We'll discuss exactly what targets are in a couple of minutes. Also, the config file contains information about the dependencies of this project, what third-party libraries it might use. So today, it's all about how do we write one of these CMakeLists.txt. How do we actually use CMake for our own project? It's worth pointing out that this .txt is a lie. I suspect that this is a historical thing that we're lumbered with. It's not a plain text file. You can't just put any old, can't write a novel in there. It's a file which is read and interpreted by the CMake executable. It's written in the CMake language. It's kind of like source code in its own right, despite the .txt extension. The CMake language is extremely capable. It's one way of putting it. It can do an awful lot. It's Turing complete, and it's got functions and macros, and it can do really, really complicated stuff. Too much, some people would say, because you can write really, really, really confusing build systems with it that nobody else can possibly understand. I have to confess, I'm absolutely not a CMake expert. There are many, many, many people who know vastly more about it than I do. CMake is one of those things where I know enough to do the things that I need to do. The same goes for Git. I said this when we were covering Git a couple of weeks ago. I have a sort of working knowledge of it, which I'm trying to, today I aim to pass on to you. CMake is extremely powerful and can be extremely complicated, but just as with Git, you can get away with just knowing a few commands, knowing enough to get by, which is the aim of today. The other thing that's worth saying about CMake lists is that for large projects, you don't have to have one monolithic, 1,000-line CMake list.txt. You can break it down and include other config files that are in subdirectories, and that's a very common thing to do, actually in even moderately sized projects. I was going to give an example of that today, but again, it's another one of those things I just didn't have time to cover. But if you want an example of that, then many of the projects on our GitHub, so github.com/CPP London Uni, all of those projects use CMake, and many of them will use one of these included CMakeList.txt from a subdirectory. So let's have a look at the simplest possible, or almost, not quite, nearly the simplest possible example of CMakeList.txt, but the simplest example that actually does something useful. So if you could all point your browsers to that URL, github.com/cpplondonuni/basic_CMake. And you'll see that it has two files in it. A CMakeLists.txt and another one called hello.cpp. You can have a look at hello.cpp if you like. It doesn't do very much. The one we're interested in is the CMakeLists.txt, obviously. So if you've got that open in your browser and you have a look at it, you'll see the first line in there looks like CMake minimum required, brackets, version 3.1. Can anybody take a wild guess at what this does?
It's the minimum make version required to install.
Almost. Not quite the minimum make version. Because, of course, your CMakeList.txt, it doesn't know anything about which particular generator it's going to be called with. So make is one of the generators that's used on you. Exactly that. It's the oldest version of CMake that this config file supports. So this is saying we require at least version 3.1 of CMake to build this project.
Anyone guess why you would, when you have to set it, but can anyone guess why you would pick a particular version? Sorry?
From one version to other, like could you compare them?
Yes, essentially. So if you support older versions, you're allowing people with older editions of CMake to use your project. However, you're then restricting the features you can utilize.
Well, what kind of features would there be if you're just building? So your compilation.
Well, as CMake evolves, I'd imagine it includes more and more stuff. That's what versions are for. So, yeah.
Is there no way of making it dynamically choose the correct version, most apt version?
Is there no way of making it choose?
Dynamically, like, okay, this thing, like I don't know if you were saying, okay, features on this are not the latest, so I'm going to use that one.
I believe there is a way of saying, okay, if I'm using, CMake 3.9, then do this. Otherwise, do it this older way. This is saying this is the absolute minimum that's required, to build this, for CMake to understand this config file. Because as I say there, newer versions of CMake come with newer features, newer commands that older versions are going to reject. So the alternative to this is just, well, an old version of CMake comes across an instruction that it doesn't understand and says, I don't know, this is a syntax error or something like that. If you put this line in, CMake minimum required with a version, then instead the old CMake versions will go, nah, I'm too old, go to this URL and upgrade. So it just gives like a friendlier error message to people who are using old CMake versions. It's actually not required that you put this line in. Again, it's sort of a helpful thing to people who are using old versions. It's a little bit more than that because it actually changes some of the defaults. So newer versions of CMake use different, what they call policies, to old versions. So this actually says we want the version 3 policies as well. So it actually does a little more than just give friendly error messages. But it is not required. If you omit it, you're just going to get the most up-to-date policies, and who cares about people who aren't bang up-to-date. It's not required. It is recommended, and if you don't include it, CLion will nag you about it. So yeah, just put it in there and shut CLion up. In particular, there are quite big changes between CMake version 2 and version 3, as you might imagine, for a major upgrade. The config file format wasn't changed or anything like that. There is a high degree of backwards compatibility, but it's not absolute. And in particular, in CMake 3, there's much better support for per-target properties, which is the recommended way of of configuring your project these days. People talk about modern CMake in the same way they talk about modern C++. And well, as far as I can gather, what they mean is version 3 of CMake. So I tend to to be honest, I don't exactly know what the difference is between every particular version of CMake, but I just chuck version 3.1 in there usually just for safety, and that seems to be fine. Someone can tell me exactly when version 3 was released, but it was many years ago now, so yeah. So the next line of our CMakeLists.txt. It's this line, project, brackets, CMake example, CXX. Anyone want to take a wild stab at what we might be doing on this line? CXX means C++, correct. As usual, because the plus character in many programming languages is kind of special. It can't be part of an identifier. You can only use letters and numbers. So it's very common to refer to C++ either as CPP or CXX. Think of it as a plus that's fallen on its side if it helps.
So how do you do for the C hash? Because C hash
They spell it C#, usually.
C hash is 4 pluses.
That's so Microsoft claim. But no,
4 pluses. 1, 2, 3, 4.
yes, allegedly C# is C++++, which I don't really understand, because if anything, it's Java++, but anyway. That's not really relevant to CMake. But yes, for things that use C# but can't use the sharp or the hash character, they often spell it the word sharp, S-H-R-P, S-H-A-R-P.
Did anyone figure this out then? What they think it's doing? Yes, you're declaring a project called CMake.
Yes.
I did just want to throw in a small caveat because it's hurt me and others. If you end up using some C libraries with your C++, this ends up biting you quite sharply because you're missing C, right? If you want to support both C++ and C, you would write CXX, of course, space, and then C. And if you don't do that, and then try to use some C library, you're going to get really weird, completely meaningless messages, and it's all because you missed one character out of this line. So if you think there's the remotest possibility you might do some C, and if you don't, it doesn't matter. Just put CXX space C, just for good measure.
Yeah.
Why isn't C++ backward compatible with C libraries?
Is C++ backwards compatible with C libraries?
You can include if you include some C libraries when you compile the C libraries.
Okay. You are correct that C++ is backwards compatible with C libraries. C++ can call C functions natively. It can use C structs natively because it has the same layout, at least for what are called pods in C++. What you can't always do is take some C code and compile it and have that C code have the same meaning as C++. You cannot in general anyway, take a C file and just give it to a C++ compiler and say compile this. Because although C++ started off as a sort of set of extensions to C, the two languages have diverged over the past 35 years.
Let's say if you do include whatever stdi or whatever. Right?
Yeah.
C,
Include a C header.
yeah, include a C header.
Yeah.
But you still need to put C there. No, you wouldn't.
Not to use a C header, but actually most C headers are written very carefully so that they have the same meaning in both C and C++. They'll use what are called extern C guards. So if they're seen by a C++ compiler, they have these macros that expand to put things in an extern C block, and they'll be careful not to use any C99 facilities and not to use any constructs that have a different meaning in C and C++. They're written in what's called the common subset of C and C++. Yes, Mike?
Technically, whenever you're using the file extension H instead of HPP, you are actually writing C.
No.
Well, I mean, usually your environment would recognize it as
Yeah, so this is something that can be a bit unfortunate. Is the extension .h is commonly used for C headers. And when you see a .h file, most IDEs or editors will recognize that as a C header file. Unfortunately, there are many people who use the extension .h for C++ headers as well. This is a really, really common thing to do. In fact, for reasons that are beyond my understanding, this is the recommended way to do it if you go and look at the C++ core guidelines, which yeah, it's confusing, and I much prefer using the extension HPP for headers that I know are C++ and .h for headers that I know are C or common subset. But there are a lot of projects that will use .h for C++ headers anyway, and if you try and read them in C, it will get hideously confused.
To just try and inject the reasoning behind it, is also why I do that. It's a matter of separation. So if you should be organising your code in such a way that it doesn't matter that you call all your C++ headers.h, because the only thing that can exist in that project is C++. If you need to write some C code as well, fine. Don't embed that in the same project. Keep it physically distinct. Organise it into some separate folders. Just keep it away, right? And that way you know, oh, this is a C project. So it doesn't matter that it's .h because everything is just C. Oh, this is a C++ project. So you again just implicitly know all the headers are going to be C++. So prefer project separation than relying on file extensions to figure out what's what, basically.
So,
What if you're writing shaders in
HUSL.
if that didn't come out on the microphone, Ollie's point is that in general for sort of well-written projects, I guess, or well-organized projects, it shouldn't really matter whether your .h contains C code or contains C++ code, because they should be organized so that they're distinct, and it should be kind of obvious from the file layout or the context which one it is.
And this is also not in contradiction of what I was saying about specifying CXX and C in the project line up there, because obviously, again, if you've done this properly,
I will talk about that in just a sec.
Got it.
Yeah, so you can have C and C++ files in the same project. You just don't embed. So they're in the same code block. Yeah, okay.
Yes, you can have both C and C++ files in the same project.
Two different projects.
And in fact, you can have headers in common between them. That's how you would call C code from C++.
So can you overload headers then?
Overload headers.
One C or one C++?
Well, so this is what I was saying to Saad. You can have headers that are carefully written in what's called the common subset of C and C++. So although they're distinct languages and they have diverged to an extent, there is still a subset which is common to both. So you can write, as long as you're careful not to use any C99 facilities, and you're careful not to use any C++ facilities, and you wrap a couple of things in macros, you can have a header file which is understood with the same meaning in both projects,
Right, but you
or
can't,
both languages.
You can't, like I said, the compiler can't decide which header to put in, depending on what.
You
use C++ or whether you use C to write the code.
It's possible, but I don't think it would be a very good idea.
So the general way you do it is you'll see this very commonly in C code that wants to support C++. They'll have an indef __C++. And then you'll usually follow that with an extern C. So they just use preprocessor definitions. So
Yeah.
C++ compilers using the header, some extra code goes in for C++, it's just for C. That code is emitted.
Okay.
So
Right.
this confusion that you talked about right at the start was only if you can have an except a source file which is written purely in C,
Yes,
part of your project.
something that has to be processed by a C compiler. So yes, as we have determined, this project line, says that this CMakeLists.txt defines a project, and that project name is CMake_example, and that we'll be using the C++ language. A project line is required. So the CMake minimum required was optional. A project is required. It is possible to have sub-projects in subdirectories, so you can sort of have more than one project, but there will always be exactly one master project, which is the one defined in the CMakeLists.txt in the root directory. So again, I won't be talking about it today, but it is possible to have sub-projects, but it's a bit more advanced, and we won't have an example of it today. But your main CMakeList.txt should define what the project's called, and probably define what languages it's written in as well. It's actually optional. You can omit the CXX. So what does this language specification actually do? I should point that out. If you put CXX in the project, it tells CMake, okay, this project uses C++. So it will go ahead and it will configure a C++ compiler. It will look for a C++ compiler on your system, and it will give you an error at configuration time if it can't find one. So if you actually read the outputs, it will say, you know, I found Clang version 3.9 or whatever it is. It might even tell you the path that it's found the compiler at. So you can specify multiple languages. You can have projects, my project, CXX, and C, in which case, when you configure CMake, that's step one of our build process, it will look for a C++ compiler, and it will look for a C compiler. And then you could specify Fortran, or you could specify Ada, or you could specify COBOL, or whatever other languages you have decided to use in your project, because CMake supports many of them. It's heavily used for C++, but it actually supports an amazing variety of languages.
So are you doing the CXX, is that just reducing the size, or is that optimizing the use of the compiler? Or are you just reducing the size of your program?
It's not reducing the size of your program, no. All it's doing is if you put CXX in there, then CMake won't bother to look for a C compiler and won't test that the C compiler works okay. So it just saves you a little bit of a few seconds of configure time. That's all it really does. There are various other things you can include in your project directive, project command, if you really want to. So you could specify the version number of the project. That's useful if it's a library project that other people depend on, because you can means the other people can specify a minimum version number that they're compatible with, or an exact version number that they require. You can also add a description and a project homepage and stuff, and that gets used. I believe that gets used if you're using CPAC, right? Things like the project homepage, and you can put a text description and things like that, which I believe, yeah, if you use this CMake extension called CPAC to produce packages, things like Windows installers and RPMs, then that information will get used in that. So a slightly more verbose version of the project command might look something like that. And you could put the word languages in that top example if you wanted to as well. So the last line of our CMakeLists.txt, the very simple example one, it's only 3 lines. The third line is the most interesting. It's this, add executable, hello.cpp. So, for the last time, a wild guess as to what this line might be doing. It's going to create an executable file with this source file, from that source file.
Sorry for wrong execution.
Yep. No, you're absolutely right. This is going to create an executable, that is a program, something you can run, called hello, or hello.exe on Windows. And it's going to create that from the file hello.cpp.
Which means you must have a main in hello.cpp.
Absolutely, you must have a main in hello.cpp, otherwise you're going to get linker errors down the line. So this line, add executable, defines a target, something CMake calls a target, and that target is named hello. So an executable is one of two types of targets that CMake supports. Well, three technically, but we're only really interested in two. We can either define an executable target or a library target. And a single project usually does, have multiple targets. So in this very simple example, we have one target. It's an executable target, and it's called hello. And it's built from a single source file called hello.cpp. Any non-trivial project is likely to consist of multiple targets. Even if you're just writing a library, or especially if you're writing a library, you will want to have some tests, and those tests will need to be compiled into an executable. So you'll probably have a test my library executable target defined, for example.
Also, before we go on, the file names of your target, in this case hello.exe on Windows, by default it is the same as the name you give the target. But it doesn't have to be. You could call it hello internally in CMake and have it spit it out as something else.exe, whatever you want. There's a property you can set to customize.
Oh, yes. So that is worth pointing out. So the first hello in this example is the target name. And by default, the name of the executable is the same as the name of the target, or has .exe put on the end on Windows. But it is, as Ollie says, it is possible to customize this. You can search the CMake documentation for the various options. You can put to add executable, or you can, as we'll see in a minute, you can set the properties of a target. And you'll be able to change the particular property for the hello target to actually specify exactly what the generated executable should be called. So let's expand on this thing about targets a little bit. Targets, or build target as should properly be called. It's a single thing that should be produced, a single end product that should be produced as part of the build. So remember, we were talking about this last week. You're going to have lots of byproducts, lots of these .o files, perhaps some generated headers, perhaps some resource files that get compiled in. You're going to have a lot of build artifacts. But all of those are sort of a byproduct of producing the target. The target is the thing we care about. Now, as I mentioned on the last slides, CMake supports two kinds of targets: executables and libraries. Well, okay, there's technically a third type of target. It's called a custom target.
The fourth one.
Is it?
Really useful, which is what we call an intermediate. Think of it as an intermediate target. It's really useful because there I have my unit tests and my actual executable. Usually I've got a bunch of C++, bunch of code, right, that they're both using. You can have all the source code get sent to this intermediate target, which is obviously just .o files. But then both your test target and your production target can both reuse all the .os. I'll find the name of it, but that's another.
Okay, well, apparently there is a fourth kind of target as well, but hey, you learn something new every day. Yeah, so there are these things called custom targets that let you have a sort of, a target that does whatever you want it to do, whatever you specify it to do. That's a bit more advanced. I'm aware that they exist. I've never actually used them, so I can't really tell you any more about them. Ollie probably can, if you're really curious about custom targets.
Custom target is basically usually just run some command to do something.
So we've just seen the add executable command to add an executable target. It should hopefully come as no surprise, there's a corresponding add library command to define a library target. And a target is defined, is built from a number of source files. So on the last slide, we saw add executable hello, and then hello.cpp. So in that case, it had one source file, but it's possible, or common, usual, to have a number of source files used by each target. And again, we usually specify these in the add executable or add library command. It is possible to set the what's called the sources property later to add extra source files to it, or to conditionally, maybe when you're compiling on Windows, you want to use this source file. If you're compiling on Mac, you want to use a different one. You can do that by setting target properties that we'll talk about in a second. Yes?
Just a question. If hello, use hello.cpp as a source file.
Yes.
We say you can have multiple source files. Will you create other lines, or can you do like in the parentheses hello space hello cpp and then space and then some other source file to add to it?
You can split it onto multiple lines. Is that what you?
What is usually done? What is commonly done?
Oh, you stick them all in. They all have to go in the executable line.
Into one.
It doesn't have to be physically on a single line in your CMakeLists.txt. You can write.
Imagine you could do add executable parentheses hello and then do it together.
And then new line.
But could you do it in one line where you add all the sources for the hello, basically?
So CMake, think of the CMakeList.txt as being like source code. So just like C++, the CMake interpreter doesn't really care that much about how your source code is laid out.
I was just curious as how is it commonly done?
I can explain this in the most succinct way possible. You type add executable, you have an opening parentheses, right? You can now keep on writing, you write the name, and then the source files. You can keep on writing those all in one line or break it up into multiple lines. CMake doesn't care. It just cares where you put the closing parentheses, right? So it's opening parentheses, all stuff, be on one line.
I understand that. I was just asking about the clarity. Like you as a developer, what do you usually do?
Oh, I see what you're saying.
I tend to put them each on their own individual lines.
Okay, so that's what's usually
unless if I've only got two of them, say I might put them on one line just so it's neater. But if I've got 20, if I've got 50, obviously I'd, yeah. And I'm actually, because I'm really sort of pedantic about this stuff, I often put them in alphabetical order just to be really annoying to anyone who's editing it. Yes, Sard. Oh, sorry. Did you have a question there? Yeah. Oh, sorry. Yeah.
Just out of interest, the add library, would that be something like a DLL?
Yes. So a DLL is a shared library. So libraries. I was going to talk about this today, but then decided against it. But libraries actually come in two flavors. Static and shared. DLL is the extension given to a shared library on Windows. So yes, a DLL file is a type of library, and CMake's add library command can produce those for you. I think it defaults to a static library, but you can request it to build a shared library.
So
Yes.
that would be a .lib, for example.
Yes, exactly.
Static. That would be static.
Yeah.
All of it, how does what is the succinct definition of a library?
A library is a bunch of precompiled functions that you can call.
So that includes stuff.
A library is not a product, right? An executable is something I can run. A user will physically use something executable. A library is for some other developer to use.
So that you can include a link with the hash include.
No, hash include is not used. Hash include is used for headers. That's a source thing. So libraries are consumed by the linker. So if you were here last week,
8 months ago when you.
well, I also did it last week. So if you can go back and have a look at that, or I can, if we've got a bit of time at the end, I'll dig up the slides again for you. But our sort of compilation model is that we'll pass each source file individually to the compiler. The compiler will spit out these .o files. And then another process called the linker takes all the .o files along with any libraries that you're using and links them all together into a final executable. So libraries are precompiled bits of code which are used by the linker to satisfy function calls that you have put in your source code. Does that make sense? Excellent.
And then one very last question. Why would you have multiple executables in a project?
Why would you have multiple executables in a project?
Wouldn't you be compiling all your source code, multiple different source files, multiple different folders, if you want executable to run them?
Oh, sorry, I didn't hear that last bit.
I think Ollie mentioned that you can have multiple executables
Yes.
as when you add the executable in a project. Why would you have multiple executables?
Why would you have multiple executables? Well,
What scenario?
yeah, so a common reason to do it would be you have a library project. Obviously, you want to have tests for your library. It's very common to write your unit tests as multiple small executables, or perhaps sometimes even not so small executables. So you might, you could have 100, maybe 1,000 different executables, each testing a separate little bit of the functionality of your library. And the advantage to that approach, rather than having one huge monolithic test executable, is that less stuff needs to rebuild when you make a small change or relink. So yes, it's possible, not even all that unusual, to have hundreds of test executables. You get projects which have lots of examples. You can find sort of game engines online that might have dozens of examples that they come with. That, those would be each one would be defined as an executable target in CMake.
Is it what they do when you have like a light version and a pro version?
Uh,
They're the same installer. Like you install a program, and if you have the key to install the pro version, and if you don't have a key to install the light version, is it what they do? Two different executables.
I don't know. To be honest, I assume it would depend on how the developer has chosen to do it. There may be one executable which just doesn't allow you to access that functionality. It just disables the menu options unless you're a licensed user. Or it might be, there are physically two executables, one of which just doesn't have that stuff compiled in.
See, when I worked at Norton, what they did, they had this thing called they used to do different versions of software for different regions. So they have Asia, they have Europe, and they have all these things. Yeah. So what they did, they moved to a multi-market platform. So what that did basically, all the functionality, everything that was ever going to be involved in any market was lumped together in a massive thing.
Yeah.
So if you bought the program, if you bought the software, you had all the functionality there already.
Yeah.
But all it was, everything was controlled by keys. So therefore, you'd have a key would give you access to different things. So I think it can be done numbers of ways. In it. The way they did it was just have everything in one place. So we didn't have to build for a specific market. We just built a general platform for everybody.
Yeah.
If you all the functionality, but if you wanted to access certain parts, you have to pay for it and get a key. So.
Yeah. So yes, two different approaches to sort of. Not really related to build targets, but two different approaches to how you'd lock off a bit of functionality from your paid program.
I wanted to mention, so the target I was referring to earlier, having the intermediate object class, it's a kind of library target, in fact, called object, funnily enough.
Oh, okay.
But to also answer your question, essentially, yes, you can make your build process more efficient by utilising the add library object type. So if your unit tests are reusing the same code, which they should be, you can just have the intermediate and build that from the two, through the two executables. And finally, just to say, having loads and loads of test executables, I tend to find is the result of using a fairly primitive test framework, or barely any at all. If you use something like Google Test, I've never found a reason to do it. I just have one test executable, everything's in there, because Google Test gives you the ability to filter the tests you want to run anyway. So it doesn't make any odds to me. There's no point in having multiple executables. I just pass on the command line, only run this test, and Google Test just does it for me. So if you use a fancy framework like Google Test, just stick to one executable, it's probably
Okay, that probably didn't come out on the mic, but Ollie was just going back to what we said, what I was saying about having the possibility of having multiple test executables. He's saying that's not a great approach, and if you use a test framework like Google Test or Catch or something like that, generally his preferred approach is to have one single or at least a small number of test executables. Although I will say I have seen in the wild, in the real world, multiple dozens, hundreds even of mini test exes. So it does exist, which was Saad's question, I think. In which scenario might you have many executables? And that would be an example. Sorry. So yes, CMake supports 2, 3, perhaps even 4 kinds of targets. There are 2 we really care about, executables and libraries. Once we have defined a target, we can actually do this slightly nifty thing of saying, in our build step, in step 2 of our using CMake process, we can say CMake -- build dots, just as we would before, but we can actually add this extra option, -- target, and then the target name. So we can say CMake -- build dot -- target hello in this example. And then if we had multiple executables, for example, multiple targets, this would only build the hello target, only build that specific target and anything that target depends on. But it would make sure that that particular target was up to date. So again, this is a way of cutting down your build times. If you don't include this -- target bit, then all the targets in your project will get built when you do CMake -- build dot. So that was last week. We just saw the short version of it, but it is possible to build only specific targets if you want to. And there's actually a sort of magic target, a catch-all target called all. So you can, in fact, say, if you really want to, CMake -- build dot -- target all, and that will build all the targets in your project.
All in all caps.
Lowercase works on Unix. I don't know if it works. Windows is funny with all these things.
And also, I'm not entirely sure what it ends up doing to your, in terms of the result, because there's also an all_build. And I suspect if you run all, it does more. It may do more than simply compile stuff. It might run like a CPAC phase or whatever potentially.
Okay. So that's how we define targets, either add executable or add library. But as I mentioned, when we use these commands, we have to give it the target name, and we also have to tell it the source files that we want to use. So we might say something like add executable, hello, source1.cpp, source2.cpp, source3.cpp. In this case, I've put them all on one line so that it fits on the slide, but you could align them vertically, and you probably would if you had source 200 or whatever. So some build systems try to be very clever and automatically detect all the source files in a particular directory. It's possible to configure CMake to do this, but it doesn't do it by default.
It's not. No, it's not. No, it's not. No, it's not. You may think it is. You may find examples online that tell you that this does a regex match and it's going to do it. You're going to bite yourself in the proverbial, because it only detects new files when you explicitly run CMake again. So if you just generate a main file or Visual Studio project, whatever, and then you call make or build, whatever, nothing will happen. You can add new files, but your build system that has been generated will not know about it, because CMake only checked what files were on your hard disk when you called CMake, not when you then went and called make. So don't do this.
So, as I was going to say, it is sort of possible, kind of, to use CMake in such a way that it will automatically notice new files. The downside is that you have to rerun the configure step every time you go to build, which is really annoying and kind of a step backwards. And yeah, not very good. Strongly frowned upon, yeah, not ideal. So with CMake, you have to explicitly state which source files, or you should, by default, you do, and you really should, explicitly state which source files belong to which targets. It's also possible to include header files in this source line, in this add executable or add library command. So you could say source1.cpp, source1.hpp, source2.cpp, source2.hpp. That's possible. The CMake documentation, the CMake people recommend that you don't. CMake is actually really smart and can understand the #include command. So it will actually look, or kind of anyway, look at your source files and work out what headers your source files depend on, and make those part of your executable as well. So the CMake documentation recommends that you don't list headers in the add executable. Unfortunately, some they've changed this now, so new versions of CLine are okay. Some old versions of CLine will tend to nag you and will say, hang on, this header doesn't belong to a project because you haven't listed it. It doesn't belong to a target because you haven't listed it here, which can be a bit annoying because it can stop the IntelliSense working properly. As I say, new versions of CLine have sorted this out. If you're using the bang up to date, this isn't a problem anymore. But if you're using a version that's a year or two old, it's a little irritating. So update your CLine.
I just been putting everything in there. All the files that I'm using just go into.
Well, you only need to explicitly list your source files. And as I say, the CMake people recommend that you only list the actual source files, not headers. Did you have a question, Sadi? I had a hand up.
I was going to say, an ID like CLine, when you create a new source file, it automatically does add managers to configure CMake to add it to your build.
Yeah, so CLine, if you use their add new C++ source file or their add new C++ class, it will ask you, I think, which target. If you've got multiple targets, it will ask you which target you want to add this source file to. And it will go and pop it into the add executable line or add library line for you. I think it might also add the corresponding header as well, which it probably shouldn't do.
I do have a slightly conflicting point here, which maybe you researched it, so I'm going to just say it as it is. There is one caveat I'm aware of, which comes with not listing header files in add executable or, say, add library, whatever, which is that if you generate a target such as Visual Studio or Xcode, your header files will simply not show up in the project hierarchy. So when I've used CMake, I've usually always included the header files in the CMake list so that they work nicely when someone generates Visual Studio or Xcode projects from it. But I wasn't aware that there was anything against doing that, but maybe you found something otherwise.
Okay, so Ollie's point is that if you're using one of the sort of IDE generators, that is the Visual Studio project generator or the Xcode project generator, if you don't include your header files in your add targets command, then they will often be skipped within the generated Xcode / Visual Studio project, which obviously wouldn't be great. This probably isn't a problem with new versions of Visual Studio that support CMake directly, but if that applies to you, then perhaps it is worth. Perhaps that's why CLine does it. I don't know. I only ever use the, simple project generators. I don't use the IDE ones, so it's not something I run into. So let's talk about target properties. So we now know how to define targets. We can define executable targets with add executable. We can define library targets with add library. Once we have defined our target, we want to set properties on it. We want to give CMake a bit more information about these that it can pass to the compiler. There are many properties you can set for targets. And exactly which properties are available depends on a lot of things, including the type of the target. But the two very most common that you'll need to set are what are called include directories, that is where to find header files, and the link libraries, that is the names or locations of the libraries that should be passed to the linker during the linking step. We'll expand on this again in a second. Most target properties, not quite all of them, but most target properties are either public or private. CMake, for some reason, really likes capital letters for some arguments, and public and private are two of those. So what's the difference? Well, a private property is an implementation detail of your targets, particularly of a library target. This is something that you use privately. Perhaps it's another third-party library that you're using internally, and that external consumers of your library don't have to care about, don't have to know that it exists. Conversely, a public property is one that your public interface depends on. So for example, if you're using a third-party library and your public interface has types that are defined in that library, then that library is part of your public interface and it should be a public property in CMake. So if the outside world needs to know about it, it's a public property. That is, other people who are consuming your library need to know about it, it's a public property. If it's something they don't need to know about, it's a private property. And yes, the distinction is only really important for libraries where these things would be used transitively. For executables, public versus private doesn't really matter because nobody else is going to be linking to your executable because it's the final executable. But sometimes for some commands, CMake does make you say private or public even when you're using an executable target, which is a bit silly, but there we are. And finally, this public and private are called property scopes. There is a third one, which is the interface scope. I've used it a little bit. It's pretty much the same as public, but it's used, or in my experience, used for header-only libraries that don't have a corresponding actual physical, source library, compiled library, I should say. So yeah, unless you're particularly writing a template-heavy header-only library, don't worry about the interface properties. CMake error messages are actually quite nice and will tell you exactly when you need to use the interface scope. So there we are. Okay. Oh, I didn't expect that bit on the right to show up. There we are. Let's take a small diversion and think about project layouts. Some programming languages have one sort of dominant build system that everybody uses, and this build system insists that you use a particular layout for your source code. Or perhaps like Python, its actual import syntax requires you to use, or import semantics requires you to use a particular layout. C++ is not like that. CMake is not like that. Everybody can do whatever they like. And CMake is incredibly flexible and will support any source layout you particularly you want to use, whatever you want to, whatever you like. There isn't one that's universally accepted. Many people do different things. What I've got on the right there, though, is something that is fairly common amongst open source projects that you'll find on GitHub, and probably, a recommended approach to how you should structure your source code, unless you've got a particularly good reason to do something else.
Style, but it's another fairly common one you'll find in C++ actually is you don't really stick headers in the source file, you stick source in the source folder. You have a detail folder that include, or a private folder under include. Something under include is then your internal headers. It's include still there.
Like I said, no two C++ programmers are going to agree on exactly the way to do it, but this is a common approach. It's a common approach for a library project anyway. So you have your project directory. It has its CMakeLists at the top level. You'd also have things like your README file at the top level, and your license file, and .gitignore, and various other things that must live at the top level. Then you have an include directory. And in your include directory are all the public headers for your library. That is the header files that define your library's public interfaces, the functions, the types that your library makes available for other people to use. Then you have a source directory, usually abbreviated SRC. And that's where all of your source files live. And commonly, in my experience, but Ollie disagrees, that's also where you'd put private headers. That's header files that are useful, that are used internally by your project, but aren't part of your public interface. Then you might have a test directory, which contains all your tests. I've got just one source file in there. Commonly, of course, you may have many source files. Hopefully, you've got lots and lots of very comprehensive tests for your library. And then you might have, or it's common to have, fairly common, to have some examples, just showing off some simple uses for how you'd use your library. If you've got an executable project, this becomes rather simpler. You don't have an include directory. You probably don't have an examples directory. All of your source code would live in source, and your test code would probably live in test. And as I say, CMake is very flexible. This is one example of a commonly used structure. There are many different ways, and if you prefer doing something else, have at it. This is what I see quite often, and it's what I use. So there we are.
What about your compiled versions?
Compiled versions.
As in, how would you do your debug, release, and all that sort of stuff?
So, where does your compiled code go?
Well, you can choose, can't you?
You can choose. So I mentioned it last week, and I mentioned it at the beginning this week. What's a really common place to put it?
A bin.
A bin. Put it in the bin. A build folder. Is that what you were going to say? Sorry. Yeah. So it's very common to have to just make a subfolder of my project and call it build in simple cases, or build clang, or build GCC debug-asan, or whatever it might be. It's really common. Again, CMake very flexible. Doesn't really care where you put these things, but just common in my experience to just make them subfolders of my project, just so everything related to that project is in one hierarchy in your file system. And then you configure, as we did last week, you configure your .gitignore to ignore any folder that's got the word build in it, so you don't accidentally go committing compiled source code, which can be a little embarrassing. So this was a little aside. This was a little aside about just how you lay out your project, or how you might choose to lay out your project. And in particular, this thing about having your public header files, if you're writing a library, having your public header files in this separate include directory. So why do I mention that? Well, to go back to talking about target properties again. So when we use a C++ library, or a C library for that matter, we get header files. Header files are the bits we include in our source code. They define all the functions that the library provides, define all the types that you can use with these functions, all the classes in C++. And as we've seen many, many times, we use these headers by saying hash include something, some library.hpp. So remind me, what does hash include actually do? Copies in the code.
To the source file which you've already defined in the header.
Yes. It effectively copy and pastes the contents of, in this case, some library.hpp into our source file. And it does this recursively. So if some library.hpp also hash includes something else, then it opens up that and copies and pastes it, and it sort of does it recursively. So this means that sometimes just including one single header file can end up spewing tens of thousands of lines into the top of your C++ source file that you never actually know is there, but that the compiler sees, which is...
Does it actually copy and paste it, or does it just call the code in the file? Like if another developer would be to open after you compile it, would you actually see that in the middle, or would it like...
It's temporary. It does it like internally. It doesn't change it on disk. It just takes an in-memory copy of it.
Yeah.
Okay.
You can think of it as copying pasting. What the compiler actually does is sort of open the file, take a snapshot of it,
Yeah, okay.
hold that snapshot in memory. Yes, sorry.
Well, in the debug file, you should actually see it, that it produces the one file with everything in it.
There is a compiler argument you can specify to get it to point out what would be the resulting file
You-
with all the substitutions, but by default it won't do that.
Yeah.
It's temporary.
You can, as Ollie said, there's a way of getting, I think it's the -E argument in GCC and Clang. I don't know what it is in MSVC, but I know it's possible. You can get it to spit out the pre-processed source file. That is, so when you actually compile some C++ source code, the first thing, or nearly the first thing that happens, is the CP processor runs. The CP processor understands all these commands that begin with a hash, and it does things like macro substitution and expanding all these includes and removing bits of source code that are if-defed out and things like that. And that happens before the actual real C++ compiler ever sees the source code. And so yes, you can get C++ compilers, or C compilers as well, to spit you out the actual pre-processed source. And sometimes it's quite alarming that your like nice little 10 lines C++ program, you ask it for the pre-processed source and it's suddenly 50,000 lines of C++ code. Yeah.
I mean, it can happen very quickly when you have functions that are actually just wrapped around system calls. Like, I mean, for example, recently I was trying to rebuild my own print function with the system, and
Yeah.
you suddenly start realizing how much is actually wrapped around the single function.
Yes. Yeah, this is, This is quite a house of cards, really. Everything includes everything else, and everything includes everything else until, eventually everything becomes kernel syscalls at the lowest level. But there are an awful lot of levels you've got to get through to get there.
So it's an aggregated process, yeah?
An aggregated process. In what's that?
I throw into the thing, I grab from here, I build that. So, as you said, like when you go, you've got loads of different, if you have loads of different header files,
Yeah.
you go grab the information there, store it wherever.
Yeah.
Grab information there, store it because it's a reference and whatnot.
Yeah. So
Is that stored in a table so you don't replicate?
Okay. So what happens if you have your source.cpp, right? And this hash includes, let's say, 3 different headers. The compiler will go away and it will find the header file, like the actual physical file on your hard disk. It will open that, then it will open the second one, then it will open the third one. And then you can think of it as copying and pasting the contents of those headers. Yeah. But those headers very likely include headers of their own, sort of recursively. And what can happen, what very commonly does happen, is that perhaps somewhere deep in this recursive process, 2 headers end up including the same file. So what happens? Do we get 2 copies of the same file dumped in our... If you just did this very naively, that is indeed what would happen. And in fact, what we have to do is to guard against that. We have to use something called include guards. Which is a line of preprocessor text that effectively says, if you have seen this unique string before, just ignore the contents of this file. And again, it's kind of one of the sucky things about C++ and C, that we have to manually specify these include guards. It's sort of 1970s era technology. There is an alternative. It's something called pragma once. But it's unfortunately not part of the standard C++, even though every compiler supports it. So, yes.
But you have the include libraries and the headers in every project, or do you just link them to the library folder of libraries on your C drive that you use, like as a base?
Oh, okay.
Over
So you're saying, where do the header files actually live? That is a good question. Where do they actually live on your system? That is, when you do hash include some library.hpp, how does the compiler know where to find some library.hpp?
That's what we saw before, right?
2 options.
Aren't you putting the path?
Exactly. It knows, the compiler knows, because you have to tell it the path for where to find header files, or at least where to look for header files. This is often known as the include path or the include directory. For GCC and Clang, you specify, if you're invoking them manually anyway on the compiler, on the command line, you use the -i flag to specify the include directories for your project. Now, it so happens, to go back to John's question, that on Unix systems, or Linux at least, there is a fairly standard location for header files. It's /user/include. If you go, I don't know if you're running Linux, but if you were, you can go and look in there, and if you've got a few development packages installed, you will probably see hundreds of headers in user include. There's also user local include, which is pretty much the same thing. But we can specify any location we like. So on Linux, user include is used for things that are installed by your system package manager. But we might want to use a newer or an older version of a particular library. So we've got that library installed somewhere else, perhaps in our home directory. And then, again, if we're invoking the compiler manually, we can pass it this -i flag to say, I want you to look in this directory for header files. When you are searching for some library.hpp, look in this directory as well.
How does it know which directory?
because you tell it with the -i flag. And again, yes, on Linux at least, it will include user include. That is the standard place as well. On Windows, there is no standard location for header files, and you have to tell it every time. For standard library header files, it's a bit different. Basically, the compiler knows where they are, and you don't have to tell it. It's the short answer, yeah.
Well, one more question about moving from files.
Yes.
For example, you use some standard library, and you put standard library in your project, and you are using only one function.
Mm-hmm.
For example, from this include. When you compile your project as a release configuration, does the compiler remove all the unnecessary code from?
Yes. Yes, is the short answer. Yes. Yeah. If you compile with optimizations on, then the compiler is very good at removing what it calls dead code elimination. So yes, it all goes, and you don't have to worry about it. The only sort of bad effect is that it slows down the compilation process, because if all this recursive include business has put 50,000 lines of source at the top of your little function, the compiler's got to go through and parse and understand all of these 50,000 lines, only to then throw away almost all or ignore almost all of it. So it's a bit of a waste of time, and it's one of the things that makes compiling C++ slow. It's one of the downsides, but they're working on it, and maybe if I give this class in a year's time, we'll all have modules and be happy, and we won't have to worry about header files anymore. Yes.
I don't know if the question goes a bit too far, but while we are talking about it, does the optimization also include anywhere where you are interfacing between the kernel space and user space? Let's say usually you would have sort of safety guards that would prevent you from manipulating anything that happens in kernel space, if I understand correctly.
Going a bit away from my field of expertise, but basically no, if the guards, I assume you're talking about things like mutexes and memory barriers and things like that. No, those don't get removed in an optimized build. They're very important, and they stay. Is that what you meant, or?
Well, more kind of, am I actually a system administrator? Do I have root rights?
Oh no, that stuff absolutely stays in a release build. Yes, yeah. That's sort of built into the. That all stays definitely. Yes.
Just generally, if you were using specific headers in your project, then you've got to be careful of updating a version that's not working in your computer if you have a central sort of repository of all your include files, rather than actually having specific include files in your project that you don't, once you've made your project, unless you rev up your project, you go through the whole lot to make sure it works.
Yes. So
You have to be a bit careful.
if that didn't come out on the microphone, it's a very good question from John. Is if you have one centralized location for your include files, say you're using the user include on Linux that just uses your system package manager, what happens if one of these header files gets updated? Say you run the update from your system package manager, and it gives you a new incompatible version of this header file. What do you do? And the answer is you're in trouble. And yes, it's a problem. Can be quite a big problem, and people refer to it as dependency hell. And I'm sure that if Ollie were in the room, he'd be saying, "Oh, well, just use Gentoo because you never get these problems with Gentoo," which probably isn't true. But yes, it's a problem, and it's one of the reasons that people put forward for using, for keeping all your dependencies, for keeping a local copy of all your dependencies, because then you can decide when it's time to upgrade.
But that doesn't include some of the general ones like the STL, but they're all guaranteed are going to be back compatible.
Well, the STL comes as part of your compiler, right? So, and yes, they try very hard to maintain backward compatibility. There are things get deprecated, and then after a 6-year period of deprecation, some of them eventually get removed. But then, you've got 6 years worth of warnings, so you're probably right in that case.
So probably some of them, or if you're using one of the sort of more obscure library, then it's probably best to put that in your project.
Well, if developers are conscientious, they will make an effort not to release backwards incompatible versions of libraries. There are libraries that have 20, 25, even 30 years of continuous backwards compatibility, which is really amazing. If you're using something like zlib, it's quite amazing. The interface, or SQLite is another one. It's probably 20 years of backwards compatibility. It's really, really, really good. However, unfortunately, not all library developers are that conscientious, and some of them will go and make breaking changes. And in that case, yes, you really have no option but to use a local copy or update your application.
Always, if you do update your application, always try, if you know you've got headers, is to keep a copy of the old header just in case, I guess.
Yeah, I mean, it's C++ doesn't have a standardized package manager. So many other languages have package managers, things like pip for Python, or Ruby Gems, or Cargo for Rust, or whatever. There is no standard one for C or for C++. There are a couple that are sort of gaining some traction, but nothing's kind of got critical mass yet. But the ones that do exist, what they do is they basically download like a snapshot of the library at this time. And if an update becomes available, they will inform you about it, but they'll give you the choice of whether to upgrade that or not. Yeah, sorry, you've had your hand up for ages.
No problem, but isn't that this kind of issue that the virtual environment is actually trying to solve by creating this kind of snapshot?
Yes, so another way to get around this is to use something like a Docker image that just contains specific versions of your dependencies. That's another way of doing the same thing, kind of more heavyweight way in some ways. But on the other hand, virtualization is so cheap that it probably doesn't make any performance difference. Were you going to say something, Ollie? No?
But also, yes, I will say something quickly. If you're taking a library and you're using its source code, take your own copy, keep it. Don't just download it from the internet every time. That's a very safe strategy.
Yes, so taking your own copy is basically what all the existing C++ package managers do. And it's the safest way. Some Linux people complain that this wastes disk space in it can mean security problems because they can't patch in different, newer versions of libraries that have security fixes. That's quite a big argument that no one's really resolved yet.
Yes, that's the caveat. You are going to grab your own copies. You should also be maintaining part of the job. You need to also make sure you're evaluating fixes. Generally a lot of libraries are well behaved. They use semantic versioning. You won't break it too badly.
It's just what Trista was saying, though, you could have a 100-line piece of code that you've written in a 50,000-line library.
Yeah.
So you've got to maintain that library updates for your 100-line piece of code if you're not.
Yeah.
Exponential growth of work for a very small program.
Okay.
Yeah.
So anyway, where were we? We were talking about CMake once upon a time. Yeah. We got distracted talking about what hash include does. So yes, we're writing our C++ source. We hash include some file. How does the compiler know where to find these files? Well, it knows because we tell it. We tell it when we invoke the compiler. If we do it manually, we use this -i flag. Well, oh yes, and these paths that we use with -i, they're called our include paths, our include folders, our include directories. Now, when we're using CMake, of course, the whole point of using a build system is that we don't have to go and invoke the compiler ourselves. So what we do is we tell CMake about the include directories we want to use. And it passes that information on to the compiler via the generator, if you've been paying attention. So to do that, there's this command called target include directories, which does exactly as I say. It passes our include paths to the particular target. And each target can have its own set of include directories. Commonly does. So as I mentioned, library projects, it's pretty common, not by no means universal, but it is common to put all the public headers in a separate directory. And if we're doing that, then we can use this target include directories command I should not say add target, I should say add library. My apologies. Let me just do a ninja edit. Come on, catch up. So we're defining a library target. That library, we'd name the target my library. Say it consists of these source files, but we want to also include public headers from the include subdirectory. So that is target include directories for the target my library. This is a public property we're setting. And we want to include things from the include subdirectory, that is relative to where CMakeLists.txt is. You can specify an absolute path as well, but by default it's a relative path to where CMakeLists.txt is. Again, something we're not going to get to today, unfortunately, but we also use target include directories frequently when we're dealing with third-party source code. If you're using something like Boost, you need to tell your compiler where to find the Boost headers. If you're using SDL, you need to tell it where the SDL headers live. Pretty much the only time you don't need to do this is for your standard library headers, because the compiler already knows where they are. All right, so finally, let's talk about target link libraries. So this is the other main important target property that we often need to set. So this is the set of libraries that our target should link with. So executables can do link with library code. So remember our compilation diagram. Compilation itself is like a two-stage process. First, we produce the object files. The linker takes the object files, glues them together into an executable. And in the process of gluing this together, it also includes this precompiled library code. Those things are called the link libraries. And when producing library targets, well, library targets can themselves sort of transitively depend on other libraries. So we use the CMake command target link libraries to tell CMake that when it invokes the linker, when it invokes the linker for this particular target, these are the names of the libraries I want you to link with. Or in fact, the full path, usually, of the library. One of the other really useful things you can do, that we'll see an example of in just a second, is we can use this target link libraries command where the target is an executable that is defined in our project, and the library we're linking with is the name of a library target from the same project. That is linked to something else I am building in this same project. And this is really, really useful because all these things are defined within CMake. It means that CMake will recognize that the library is a dependency of the executable, and that if you change anything about the library, it knows it has to go and rebuild the executable because its dependencies have changed. Linking to something within the same project also has this other handy side effect. Means we don't have to do this target include directories thing for our executable. Just saves us from doing that because the CMake target, because they're public properties, it contains enough information. So let's have almost at the end now, but let's have a little look at a very slightly more realistic CMakeLists.txt. I showed you a very simple one, trivial one with just 3 lines. This one's got 1, 2, 3. This one's only got 6 lines. So 7, I lied. So you can find this project at that URL, github.com, CPP London U/CMake example. And oh yes, here's something I didn't mention. We can put comments in a CMakeLists.txt file using hash symbol. So just like Shell and like Python and various other languages, the hash character introduces a comment.
Question.
Yes.
Wouldn't it be sensible to make comments the same standard as in C++? Sorry, yeah, in C++.
This thing of using a hash symbol is very, very common in scripting languages because it's what the Unix shell uses.
Okay. Because it's like, in one you do the /.
Yeah.
Or /.
Yeah, C-like languages tend to use a double slash or a slash star for a multi-line comment. So yes, C, C++, Java, C#, all those C-type languages. But for scripting languages, it's common to begin a comment with a hash symbol instead. So Python, for example, uses a hash for comments. So yeah, this is a slightly more complete example. So the first 2 lines are the same as we had before. We're saying that the minimum version of CMake we require to build this project is version 3.1. And then we're defining a project called CMake example, and we're saying that this project uses C++ only. And this time, we're adding a library target. And I'm calling this library hello, or calling the target hello. And the source code for my hello target lives in the directory source, and it's named hello.cpp. So this is a path relative to where the CMakeLists.txt is. So if you go to that URL, you'll be able to see these files, see where they exist.
So would that be hash include angle brackets, hello, or inverted commas?
Well, I haven't told you the names of any of the...
That's not called hello.
Well, this is hello.cpp. This is a source file. Actually, if you were to go and look in this include directory, you'd see that there's a file called hello.hpp. And you would include that with angle brackets, yes. Yeah. So target include directories, hello, it's a public property. That is, everybody who uses my hello library needs to know about these public headers, and they're in this include subdirectory. And then, just to show off really, I'm using this target compile features command. So this is another way of setting particular properties on a target. So I'm saying that when I'm telling CMake, when you compile the hello target, I want you to set the compiler to C++14 mode. And this is a public property. So anybody who uses this library must also have their compiler set to at least C++14 mode. There are various other commands that can be used to set target properties, including set target properties itself, which is the most general. But there's things like target compile definitions is another one. These are all covered in the CMake documentation, of course. So these 3 lines in the middle are defining a target called hello, a library target called hello. They're setting the include directories, or the include directory in this case, for the hello target. And then we're saying, oh, I want C++14 mode. Actually, if you go and look in that source file, there's absolutely nothing that requires C++14. I just thought I'd show you how to do it if you were curious. We then add a second target. This time it's an executable target, and it's called test hello. And the source code for this second target is in a subdirectory called test, and it's a file called testhello.cpp. And then we say to the compiler, or we say to CMake, rather, I want you to link the hello target, the hello library, with my test hello executable. That is, when you are compiling, when you are linking the test hello executable, I want you to include, I want you to link with the hello library. So this, on the bottom line, the hello refers, in this case, to the CMake target. Does this make sense? Does everybody understand what's going on? Or are you just falling asleep because I've been nattering on about CMake for the last hour and a half and it's boring? Fairly clear what's going on? Yeah.
The compiler features is translated into flags.
Yes.
std14 is dash for std equals 14.
Yes. So so CMake knows how to talk to various compilers, and it knows how to set, knows the right compiler flags to set these things. So yeah, if you're using Clang or GCC, this would use dash standard equals C++14. And if you're using the Microsoft compiler, it would use whatever the equivalent flag is that I've forgotten off the top of my head. But yes.
So the add library in the hello, src hello.c, putting that hello in there means you need, when you call it, I was just looking at your code, that means you need to put hello, colon, to actually call it.
No.
It's not a class definition.
No, this is nothing to do with. This is nothing to do with C++ at all, right? This is right because CMake is a build system for many languages, not just C++. You can use it to manage C source, which knows nothing about namespaces, or Fortran source, or Ada source, or whatever language. So it just so happened that if you go and look in that file, I used a C++ namespace called hello.
Yeah. So when
But that's coincidence.
okay, so when you say add library, the first hello, what is that
That is the name. Well, it's the name. You are correct, but yes, it's technically the name of the CMake target. And by default, when it produces the library, it will give that library the same name as the CMake target.
And so that's when that's like you're defining it there. So then you can use it later on in that target include directory target.
You are defining it there so that you can use it later on. Exactly that.
Okay.
Absolutely correct. Yes.
So within the source code itself for test.hello.cpp,
Yep.
would the user have used some things from that library?
Within the source code, so the question is, within the source code for testhello.cpp, you can actually,
I'm just asking a very hypothetical question.
yeah.
But what, like, would there be like an include thing that they would use to use some things from that library? Or how would they invoke something from it?
Okay, so the question is, how would they invoke something from the hello library? So if you can actually go and have a look at the source code of testhello.cpp, it's just at in that repository at the top. And what you'll see in there is the top line is hash include, angle brackets. I think it's just hello.hpp, isn't it? Yes. Right. So hello.hpp is a file that is defined in the include directory. And that includes the definition of a function, which I think is just called say hello, if I remember rightly.
Yes.
In the namespace hello, yeah. So this header file has the declaration of a function. It doesn't have the definition of the function. The definition, that is the actual code, the code of the function, what the function does, lives in this file hello.cpp. So when we produce the hello library, libhello, as it will be called on Unix systems, the compiler goes away and it compiles hello.cpp, and it puts the resulting compiled machine code of the say hello function into this library, this .a file or .lib file, depending on which system you're using. Then later on, we're compiling this test hello executable. And in this case, the compiler reads the header file. It says, okay, I know, it sees the declaration of the say hello function. It says, okay, I know that a function called say hello exists. I know its name, I know its return type, I know the number of arguments, and the types of those arguments. It has all the information required to call this function. It doesn't know what it does. It doesn't have any clue about the implementation of this function. All it's seen is the definition. But that's enough for the compiler to produce a .o file, that is, to compile testhello.cpp, to produce testhello.o. Later in the production of the test hello, the linker gets invoked. And the linker will look at the .o file and it will say, okay, I see you're calling a function called say hello. And then it'll look at the libraries and go, oh, this library has a function in it called say hello. And then it will link your call to say hello with the definition of say hello. It will resolve that call. It will link those two bits of code together. That's why it's called the linker. Does that explain?
Yes, that's very well explained. Thank you.
Okay. Well, I didn't think I'd done enough work this week, but it turns out that it's 2 minutes to 9, which is just about perfect timing. You guys asked a lot of questions because you knew, I needed to fill a bit. So.
Is divorcing this from thinking about code as the C++ code it's very easy to try and put the two together.
Divorcing this from C++ code. Yeah, well, I guess the idea of this module is to get you to start to think about things that aren't necessarily just writing C++ code. Think about how you structure a project, to get you to think about source code management, to get you to think about build systems, or get you to know a little about build systems anyway. Nobody wants to be a CMake expert. Anyway, there are about 50 seconds left. This was in case we had any new people who didn't have this installed last week, but if you want a little exercise, hey, it did this last week, didn't it, with the exercise slide? Don't know what's wrong with it. If you want to have something to do over the next week, then you can go to that URL, pad left no CMake. Now you remember our little pad left, our stupid library we were playing with when we were playing with GitHub. This was this stupid library. I've taken that and I've removed everything from the CMake file. The CMake file is almost empty. And I've given you some instructions in the README file. Basically, I want you to take what you've learned today and make the CMake file work again. Define all the targets that I had before I deleted all the code in there, all the definitions in there. Right, so if you get stuck, we're here to help. Well, that might be true for about the next minute or something, but then we're all going to the pub. And of course, you're all more than welcome. Even people online, by all means, come and join us if you can make it to Moorgate in the next hour or so. But no, seriously, yes, the URL is there. Just make a note of it, and yeah, have a go at that, and maybe I'll go through the answers next week. If you really, really get stuck, of course, the original pad left repository is still there on GitHub. I didn't delete it, so the answers are there if you want to cheat. But try and have a go at it yourself, because it's good to get a bit of an understanding for what CMake is doing behind the scenes. Anyway, that's it from me. This has been a slightly different session, slightly more relaxed. I feel like I haven't powered through things as much as I usually would. We had lots of good questions today, so thank you for that. And as I say, we're all off for a beer. Please go and join us. Thank you very much.